Welcome to this comprehensive video on piecewise functions. I'm excited to guide you through this fascinating topic that bridges theoretical mathematics with real-world applications. A piecewise function is a mathematical function that uses different formulas or rules depending on the input value. Instead of having one formula that works for all inputs, we have multiple pieces, each with its own formula that applies to a specific interval. Here's a simple example of a piecewise function. This function has two pieces. When x is less than 0, we use the formula x plus 1. When x is greater than or equal to 0, we use the formula 2x. Notice how we have two distinct pieces, each with its own formula and condition. The first piece applies when x is negative, and the second piece applies when x is non-negative. Piecewise functions are incredibly useful because they model real-world situations where different rules apply under different conditions. For example, tax brackets use different rates for different income levels. Thermostats turn on or off based on temperature, and shipping costs often have different rates for different weight ranges. Throughout this video series, we'll master every aspect of piecewise functions. We'll learn how to define them properly, understand their components, evaluate them at specific points, graph them accurately, and apply them to solve real-world problems. By the end, you'll be confident working with piecewise functions in any context. Now that we understand what piecewise functions are and why they're important, we're ready to dive deeper into their structure and properties. Let's begin our mathematical journey. Now that we understand what piecewise functions are, let's dive into how we formally define them. A piecewise function is defined by multiple subfunctions, where each subfunction operates over a specific interval of the domain. Think of a piecewise function like a decision tree. When we input a value of x, the function first checks which condition that x satisfies, then applies the corresponding formula. Now let's see how we write this mathematically. The standard notation for piecewise functions uses curly braces to organize the different pieces. The general structure starts with f of x equals, followed by an opening curly brace. Inside the brace, we list each formula along with its corresponding condition. Let's look at a concrete example to make this clearer. Consider the function f of x equals x squared when x is less than 0, and x when x is greater than or equal to 0. We start by writing f of x equals, then open our curly brace. The first piece is x squared, which applies when x is less than 0. Notice how we clearly state both the formula and its condition. The second piece is simply x, which applies when x is greater than or equal to 0. Finally, we close the curly brace to complete our definition. Notice the key components. We have different formulas on the left and conditions on the right that tell us when to use each formula. Let's see how this works with specific values. If we input x equals -2, since -2 is less than 0, we use the first piece, x squared. If we input x equals 3, since 3 is greater than or equal to 0, we use the second piece, just x. This is the essence of piecewise functions. Different formulas for different input ranges, all organized using curly brace notation with clear conditions for each piece. To truly understand piecewise functions, we need to break them down into their key components. Every piecewise function has distinct pieces, specific domains, and important transition points that determine how the function behaves. First, let's understand what we mean by pieces in a piecewise function. Each piece is a separate mathematical formula that applies to specific input values. Look at this example function. This function has two distinct pieces. The first piece uses the formula 2x plus 1, and the second piece uses the formula x squared. Each piece represents a different mathematical relationship. Now let's focus on the domains. The domain of each piece tells us exactly which x values that piece applies to. This is crucial for understanding when to use each formula. The first piece applies when x is less than 0, meaning all negative numbers. The second piece applies when x is greater than or equal to 0, covering 0 and all positive numbers. Transition points are where the function switches from one piece to another. These points are critical because they determine the behavior and continuity of the function. In our example, the transition point occurs at x equals 0. This is where the function switches from using the first piece to the second piece. Domain restrictions must be mutually exclusive, meaning they cannot overlap. If domains overlap, the function would have multiple values for the same input, which violates the definition of a function. In the incorrect example, both pieces include x equals 2. This creates ambiguity because we don't know which formula to use when x equals 2. Domains must also be collectively exhaustive, meaning they cover the entire intended domain of the function. There should be no gaps where the function is undefined. The incomplete example has a gap. What happens when x is between -1 and 3? The function is undefined in this interval, which creates problems. Boundary points deserve special attention because whether they are included or excluded can significantly affect the function's behavior and continuity. We use open circles to show when a boundary point is not included in a piece's domain and closed circles when it is included. This notation is crucial for understanding exactly where each piece applies. Understanding these key components is essential for working with piecewise functions. Each piece has its own domain. Domains must not overlap, but must cover all intended values, and boundary points require careful attention to determine whether they are included or excluded from each piece. Now that we understand the structure of piecewise functions, we need to learn how to evaluate them. Evaluating a piecewise function means finding the output value for a specific input. This process involves two crucial steps that we must follow carefully. Step 1, we must identify which piece of the function applies to our input value. This means checking the domain conditions to see which subfunction we should use. Step 2, once we know which piece applies, we substitute our input value into that specific subfunction and calculate the result. Let's see this process in action with 3 examples, starting with a simple case and building up to more complex situations. Example 1. We have a piecewise function with 2 pieces. The first piece is x squared when x is less than 0, and the second piece is 2x plus 1 when x is greater than or equal to 0. We want to find f of -3. Step 1. We need to check which condition -3 satisfies. Is -3 less than 0? Yes, it is. This means we use the first piece of the function, which is x squared. Step 2. Now we substitute -3 into x squared. F of -3 equals -3 squared, which equals 9. So our final answer is 9. Example 2. Now we have a more complex function with 3 pieces. We need to find g of -1. Notice that -1 appears as a boundary point in our domain conditions, so we need to be extra careful. Step 1, we check each condition. Is -1 less than -1? No, that's false. Is -1 greater than or equal to -1 and less than 2? Yes, that's true. So we use the second piece, x squared. Step 2, we substitute -1 into x squared. G of -1 equals -1 squared, which equals 1. The key insight here is that boundary points belong to exactly one piece determined by the inequality symbols. Example 3. Our final example involves more complex expressions, including a square root and absolute value. We need to find h of 5. This shows how piecewise functions can contain any type of mathematical expression. Step 1, we check if 5 is greater than or equal to -4. Yes, it is. So we use the first piece, which is the square root of x plus 4. Step 2, we substitute 5 into the square root of x plus 4. This gives us the square root of 5 plus 4, which equals the square root of 9, which equals 3. So h of 5 equals 3. Let's review the key points for evaluating piecewise functions. Always check the domain conditions first to identify which piece applies. Remember that boundary points belong to exactly one piece, so pay careful attention to whether inequalities use less than or equal to. Finally, substitute your input value carefully into the correct expression. With practice, evaluating piecewise functions becomes a systematic process. The key is to be methodical. Identify the correct piece, then substitute and calculate. In our next section, we'll learn how to graph these functions visually. Now that we understand the components of piecewise functions, it's time to learn how to graph them. Graphing piecewise functions requires careful attention to domain restrictions and transition points. The key to graphing piecewise functions successfully is following a systematic step-by-step process. Let me show you the essential steps we need to follow. Let's work through these steps using a concrete example. We'll graph the piecewise function f of x equals x plus 1 when x is less than 1, and 2x when x is greater than or equal to 1. Step 1. Mark the domain boundaries on the x-axis. Our transition point is at x equals 1, so we need to clearly mark this boundary point. Step 2. Graph each piece on its corresponding interval. Let's start with the first piece. F of x equals x plus 1 for x less than 1. This is a linear function with slope 1 and y-intercept 1. Now let's graph the second piece. F of x equals 2x for x greater than or equal to 1. This is also a linear function, but with slope 2 and passing through the origin. Step 3. This is the crucial step. We need to use open and closed circles to indicate whether endpoints are included or excluded from each piece. At x equals 1, the first piece uses x less than 1, so we need an open circle. For the second piece, we have x greater than or equal to 1, which means x equals 1 is included. Therefore, we use a closed circle at this point. Notice how the open and closed circles work together at the transition point. The open circle shows that the point 1, 2 is not part of the first piece, while the closed circle shows it is part of the second piece. This ensures our function is well defined at every point. There are no gaps and no overlapping values. The function has exactly one output for every input in its domain. Let's verify our graph by checking a few key points. For x equals 0, which is less than 1, we use the first piece. F of 0 equals 0 plus 1 equals 1. For x equals 2, which is greater than 1, we use the second piece. F of 2 equals 2 times 2 equals 4. Perfect. Our graph correctly represents the piecewise function. Remember, the key elements are marking domain boundaries, graphing each piece carefully, and using the correct circle notation at transition points. Now that we understand the basics of piecewise functions, we need to focus on the critical aspects of graphing them correctly. The key is understanding domain restrictions and checking for continuity. Our first example shows a continuous piecewise function. Notice how we have two pieces, x plus 1 for x less than 0 and 2x plus 1 for x greater than or equal to 0. First, we graph the piece x plus 1, but only for x less than 0. The dotted line shows our domain boundary at x equals 0. Notice the open circle at the boundary point indicating this piece doesn't include x equals 0. Now we graph the second piece, 2x plus 1 for x greater than or equal to 0. The closed circle shows that this piece includes the boundary point at x equals 0. To check continuity, we verify that both pieces give the same y value at x equals 0. Both pieces give y equals 1, so the function is continuous here. Our second example demonstrates a discontinuous piecewise function. Here we have x plus 2 for x less than 1 and just x for x greater than or equal to 1. First, we graph x plus 2 for x less than 1. At x equals 1, this piece would give us y equals 3. But we use an open circle since this piece doesn't include x equals 1. Now we graph the second piece, just x for x greater than or equal to 1. At x equals 1, this gives us y equals 1, shown with a closed circle. Notice the jump from y equals 3 to y equals 1 at x equals 1. This creates a jump discontinuity because the function values don't match at the boundary point. Our final example shows a more complex piecewise function with three pieces. We have negative x for x less than negative 1, the constant 1 for x between negative 1 and 2, and x minus 1 for x greater than or equal to 2. We have two boundary points to consider, x equals negative 1 and x equals 2. The dotted lines help us visualize these domain boundaries. First piece, negative x for x less than negative 1. At x equals negative 1, this would give y equals 1, but we use an open circle. Second piece, the constant function y equals 1 from x equals negative 1 to x less than 2. Closed circle at negative 1, open circle at 2. Third piece, x minus 1 for x greater than or equal to 2. At x equals 2, this gives y equals 1, shown with a closed circle. Checking continuity. At x equals negative 1, both adjacent pieces give y equals 1, so it's continuous. At x equals 2, both pieces again give y equals 1, so it's also continuous. This function is continuous everywhere in its domain. Remember these key points when graphing piecewise functions. Graph each piece only within its specified domain. Use open and closed circles correctly to show inclusion or exclusion of boundary points. Always check for continuity at transition points and look for any jumps or breaks that indicate discontinuity. Now, we'll work through a complete example that combines both graphing and evaluating a piecewise function. This will help solidify your understanding of how these functions work in practice. Our piecewise function has three distinct pieces. The first piece is negative x when x is less than negative 1. The second piece is the constant value 1 when x is between negative 1 and 2. The third piece is x minus 2 when x is greater than or equal to 2. Let's examine each piece carefully. The first piece, negative x, applies when x is less than negative 1. This means we use this formula for all x values to the left of negative 1 on our graph. The second piece is the constant function y equals 1, which applies when x is greater than or equal to negative 1, but less than 2. Notice the closed bracket at negative 1 and open bracket at 2. The third piece, x minus 2, applies when x is greater than or equal to 2. This covers all x values from 2 and beyond to the right on our graph. Now let's graph each piece on the coordinate system. We'll start with the first piece. F of x equals negative x for x less than negative 1. Notice the open circle at x equals negative 1. This indicates that the point negative 1 is not included in this piece of the function, since our condition is x less than negative 1, not less than or equal to. Next, we graph the second piece. F of x equals 1 for negative 1 less than or equal to x less than 2. This is a horizontal line at y equals 1. Here we have a closed circle at x equals negative 1, showing that this point is included in the second piece. We also have an open circle at x equals 2, indicating that this boundary point is not included in this piece. Finally, we graph the third piece, f of x equals x minus 2 for x greater than or equal to 2. This is a linear function with slope 1 and y-intercept negative 2. The closed circle at x equals 2 shows that the point 2, 0 is included in this piece. Now we have our complete piecewise function graphed with all three pieces clearly visible. Now let's evaluate this piecewise function at three different points. The key is to first determine which piece of the function applies to each x value, then substitute into the appropriate formula. First, let's evaluate f of negative 2. Since negative 2 is less than negative 1, we use the first piece of our function, f of x equals negative x. So f of negative 2 equals negative times negative 2, which equals positive 2. We can see this point clearly marked on our graph. Next, let's evaluate f of 0. Since 0 is between negative 1 and 2, specifically negative 1 is less than or equal to 0, which is less than 2, we use the second piece, f of x equals 1. Since we're in the constant piece, f of 0 simply equals 1. This is straightforward because the second piece is just the horizontal line y equals 1. Finally, let's evaluate f of 3. Since 3 is greater than or equal to 2, we use the third piece of our function, f of x equals x minus 2. So f of 3 equals 3 minus 2, which equals 1. Notice that both f of 0 and f of 3 equal 1, but they come from different pieces of the function. Let's summarize our results. F of negative 2 equals 2 using the first piece, f of 0 equals 1 using the second piece, and f of 3 equals 1 using the third piece. Each evaluation required us to first identify the correct piece based on the domain conditions. This example demonstrates the complete process of working with piecewise functions. Carefully graphing each piece with attention to boundary points and systematically evaluating the function by first determining which piece applies to each input value. Now that we understand how piecewise functions work mathematically, let's explore how they appear in the real world around us. Piecewise functions are incredibly powerful tools for modeling complex phenomena that behave differently under different conditions. Our first example is income tax brackets. Most tax systems use progressive taxation, where different income ranges are taxed at different rates. This creates a perfect piecewise function. Consider a simplified tax system with three brackets. Income up to $20,000 is taxed at 10%. Income from $20,000 to $50,000 is taxed at 20%. And income above $50,000 is taxed at 30%. We can express this as a piecewise function where t of x represents the tax owed on income x. Notice how each piece applies to a specific income range, and the function changes its behavior at the boundary points. Our second example comes from engineering and everyday life: thermostat behavior. A thermostat maintains temperature by turning heating or cooling systems on and off based on current temperature readings. Imagine a thermostat set to maintain 70 degrees Fahrenheit. If the temperature drops below 68 degrees, the heater turns on. If the temperature rises above 72 degrees, the air conditioner turns on. Between 68 and 72 degrees, the system remains off. This creates a piecewise function where the output represents the system's state: +1 for heating, 0 for off, and -1 for cooling. This discrete switching behavior is perfectly modeled by a piecewise function. Our third example comes from electrical engineering: battery charging behavior. Lithium-ion batteries charge differently depending on their current charge level, following a multi-stage charging protocol. A typical lithium-ion battery uses constant current charging when the battery is below 80%, then switches to constant voltage charging above 80% to prevent overheating and extend battery life. The charging current can be modeled as a piecewise function, where I represents current in amperes and C represents the charge level as a percentage. This ensures optimal charging while protecting the battery. These examples demonstrate the versatility of piecewise functions. They excel at modeling systems that change behavior based on different conditions or thresholds, making them essential tools in engineering, economics, computer science, and many other fields. In conclusion, piecewise functions are powerful mathematical tools that allow us to model complex phenomena by combining different functions over different intervals. They provide precise and adaptable representations for systems that change behavior under different conditions. From tax calculations to engineering systems, from computer algorithms to scientific models, piecewise functions help us understand and predict the behavior of complex systems in our world. Thank you for joining me in exploring piecewise functions. If you found this helpful, please like this video and subscribe for more mathematics tutorials. Leave a comment if you have questions or suggestions for future topics. Keep practicing, and remember that mathematics is all around us, helping us understand and model the world we live in.